Hi everyone. In this video we're going to start discussing section 4.3, which is about quadratic functions and their properties. So the difference between section 1.2 and section 4.3 is that in section 1.2 we were talking about quadratic equations. So we had a quadratic, which is a polynomial with a leading term of x squared, and then an x term possibly, and then just a number. But now we're talking about quadratic functions. We don't necessarily need to set that equal to something. We're just looking at how that function behaves, okay, and their properties. So, definition, a quadratic function is a function of the form this, f of x is equal to ax squared plus bx plus c. So my function is ax squared plus bx plus c. Okay? A, b, and c are real numbers, and a isn't equal to 0. If it is, then there's no x squared term, and then we're dealing with linear functions, not quadratic functions. Okay? The domain of a quadratic function is the set of all real numbers. Okay? So when I look at a quadratic function, any number is able to be plugged in or substituted into this equation here, and there's no point at which it looks like this function is stopping going this way or this way. So the domain is all real numbers for any quadratic function. Here are some properties of a quadratic function that we're going to be interested in. One is its concavity. Okay. So we'll talk a little bit about the concavity of a function, its vertex, and its axis of symmetry. Okay, so concavity is how the parabola opens up. Okay, so if you view this picture of the quadratic over here, you can see that the graph looks to be opening, okay, from a bottom to top, or it looks like it's opening upward. And so we're going to call any quadratic function that opens upward concave up. Okay? So it looks like a U. Conversely, if you have a function that looks like, well, that's not as good. There, if we have a function that looks like that, it looks like it's opening downward, and so it would be concave down. Okay, so we have concave up and concave down. And that's an important property of a quadratic function because it sort of tells us how the function is behaving. Okay, so that's concavity. The vertex is the highest or lowest point on the parabola. Okay, so vertexes are often important because we want to know where that highest or lowest point is. Okay, for instance, in the graph up above, we have that the vertex would be here at 0, 0. It's the lowest point of the graph, and we can see that the function is increasing everywhere else, so that is definitely going to be the lowest point. Okay, there will be one lowest or highest point always for a quadratic function. Okay, so quadratic functions will always have one of them. And if we wanted to think back to the material on the last exam, we would have called this an absolute minimum. Okay, and then similarly, if I had this point here, that would be my vertex, we would call that an absolute maximum. So these vertices have something to do with maximum and minimum points. It's the highest or lowest point on the parabola. Okay, so that's a vertex. And then lastly is the axis of symmetry. Quadratic functions will always have this shape that you see above, okay, a U or an upside down U. It'll vary in how squished or stretched it is, but it'll always have this basic shape. And the axis of symmetry is the line that cuts the parabola in half. And so if you'd fold one side of the parabola over on the other, then you would only see one picture. And so you can see in this graph up here, this is the axis of symmetry, because if you cut it at x equals 0, you'll see that when you fold it over, there's only one sort of picture. Okay, so it's symmetric. The graph is symmetric around that line. And we've had some practice with this in our even and odd function discussion. Remember, even functions are functions that are symmetric around the y-axis. Okay, so let's look at an example. 2x squared plus 8x plus 5. Okay, so we have an example here, and then we have the graph of that function. Okay, we see right away that it is definitely concave up. Okay, concave up. Its vertex looks to be at -2 and -3, so the point -2, -3, and the axis of symmetry seems to be around 2. Okay, so the axis of symmetry is x equals 2. -2. So what I want to do here is I want to look at the form of the equation up here. This is what I mean, and see if that can sort of give us some idea of what the graph is going to look like in terms of concavity, a vertex, and an axis of symmetry before we actually graph the function. Right? And so it turns out that each one of these has to, of course, do with the coefficients out in front of the x's, or just the coefficient with no x, which is here is 5. Okay, they all have something to do with how I determine each of these. So let's look. So for a quadratic function, ax squared plus bx plus c, we have the following pieces of information. If that leading coefficient is greater than 1, then we have a concave up graph. So if you go back to this example, you'll see that 2 is, of course, greater than 0, so it's lifting up, so concave up. If that was a negative number out in front, it would be concave down. Right? So there's that. The vertex always happens at opposite b over 2a. Okay, so the x-coordinate of the vertex is -b over 2a, and then the y-coordinate we find by substituting -b over 2a into the function that we want. So if we look back here, -b over 2a is -8 over 2 times 2, which is 4, and so then we get that -b over 2a is -2, which makes sense, right? Because here's -2, the x-coordinate of the vertex is -2, okay, we found, and so we can substitute in -2 into the equation, and what you're going to get out is -3. Okay, so that's how we found that vertex. And then last is the axis of symmetry. And the axis of symmetry is the same as the x-coordinate from the vertex. So let's do an example. All right? So if I have the function, oh, well, I guess I picked a non-fun one here because we just did it. But actually, I think I picked this on purpose so that we can verify what we found before. Okay, so before we were looking at it just graphically, not sort of algebraically, to find the answers to the concavity, the axis of symmetry, and so on and so forth. Okay, so first I want to find its concavity, and we know that if a is greater than 0, which it is, two is greater than 0, so concave up. Okay, so that's concavity. The vertex happens at negative b over 2a, and then the function evaluated at negative b over 2a. So we find that negative b over 2a is equal to negative, well, it is negative 8 over 2 times 2. So we get that negative b over 2a is negative 2. Okay, negative 8 divided by 4 is negative 2. So that's the first part of the vertex, the x-coordinate. And then we substitute negative 2 into the function to get a number out. So negative 2 squared is positive 4 times 2 is 8. Okay, so we have 8 plus 8 times negative 2. So really that's 8 minus 16. And so 8 minus 16 is negative 8. And then I add 5 to get negative 3. Okay, when I substitute in negative 2, I get 3 out. Okay, so that's my vertex. Okay, and then the axis of symmetry, which we already found in part B, or the vertex part, is x equals negative b over 2a, and we found that negative b over 2a is negative 2. So the axis of symmetry is at negative 2. And if we go back to our function here, we see that that matches exactly. We found the vertex. We saw that the axis of symmetry was negative 2, and that it was concave up. Okay, so that's how you do that. And so for our first your turn, sorry, I need to zoom out a little bit. I want you to find the concavity, vertex, and axis of symmetry for the function 2x squared minus 4x plus 1.